Good morning everyone, and welcome back to our channel. Let's continue with the CNC turning tutorial, and today we're looking at a fixed cycle that's essential because there are no alternatives. The alternative is G33, which is for threading, but it involves a long series of steps. On the other hand, for threading done with a tool, there's a fixed cycle, the threading fixed cycle G76, which allows you to define a thread like M10 with a pitch of 1 or M80 with a pitch of 4 in just 2 blocks. So it definitely makes life a lot easier. M80 pitch 4-1. So let's say it makes life a lot easier. It's a fixed cycle that I don't like very much because it's rigid. That is, it's not particularly interpretable. That's how it is, and that's how it must be learned. Today we'll see how Fanuc handles it, but conceptually, I repeat, it works the same way everywhere. So let me show you what threading means, which is basically a shaped insert. You can see that the tip of the insert is shaped like the crest of a thread turned upside down. Here we're going to make a series of passes with a depth of just a few tenths with a feed rate equal to the pitch of the screw. So if we do an M14 X2, we'll have an F2. Of course, it's the machine's job to synchronize the movement of the axes and the spindle so that when the tool starts, it will always fit into the groove created earlier. So it's not our responsibility to synchronize the self-centering with the movement of the axes, but our responsibility is simply to set the fixed cycle correctly. This cycle has 2 blocks. The first is a G76 with P plus 6 digits, Q and R. The second block is also a G76 with X, Z, R, P, Q and F. Assume a 20 diameter pin for N20X2 threading. Threading inserts vary for specific pitches. Inform your supplier of the pitch or check catalog data. Threading can be programmed in G96 for variable speeds. The spindle speed must be set with G97 for both roughing and finishing. Let's now look at them on the board in detail. Let's assume we have a pin with a diameter of 20 that we want to thread N20X2. As always, we will call all our parameters. So the famous G92, which I won't repeat anymore, until we get to the point where I wanted the black tool, which I prefer to call T0404. For example, the thread cutter. Be careful, the threading inserts are not all the same. Each threading insert is generally made like this, and this is the part that does the work. Each pitch, not diameter, will have a different shape for this tip. So if you go to order the inserts, tell your tool supplier what pitch you are going to use, or correctly interpret the data from the purchase catalog. Now, threading being diametrical can easily be programmed in G96, meaning I don't have to use fixed speeds, but I can easily wait. I need to check something. I have a doubt. Hold on a second. Here it is. No, I was mistaken. So I'll leave it. I won't cut this part of the video. The spindle speed must be programmed with G97 and must be the same for both roughing and finishing. G96 would, so in a thread, imperfect. Okay, I apologize. I had a lapse. asking a few questions every now and then isn't wrong. So, the movement of the spindle of the self-centering. Chuck, we said. G97 S500, for example. M3. We're going to parameterize these 500 RPM with the cutting speed. Sorry, I didn't put the video back on. So, I was writing. We're going to parameterize these 500 RPM with the cutting speed required by our tool according to the formula I showed you in the previous videos about cutting speed. After that, where are we going to position ourselves? We're going to position ourselves in rapid G0 X20 Z4, which is the crest diameter of the thread at a certain distance in X. I always recommend at least twice the pitch, and will prepare for the macro, which is composed like this: G76 P100. 60 first zeros show passes. 60 first zeros passes. So the first pair of zeros indicates the number of finishing passes. So here we can write 0, 0, 1 or 0, 2. Okay, we can't write 10 finishing passes. The second pair of zeros indicates how the tool exits. So 0, 0 is the most commonly used. So 6, on the other hand, is the other way. There are two options. When I exit, I can exit like this, or I can exit gently. 0 means I exit straight. Okay, and that's the most commonly used. The final pair indicates the threading angle, if I remember correctly. So the third pair indicates the tool entry angle when executing the thread. 60 degrees for metric threading, 55 degrees for wet work threading, and 0 degrees for vertical entry threading. So metric, wet work, and vertical entry. Then we have a Q. Now let's narrow it down a bit.
G76P that was 60. Then 6P. This is.
We have a Q, which is the minimum depth of cut.
Look, I'm reading. I'm not ashamed to make a video while I read, because you can't remember everything, for God's sake. So, it's the minimum depth of cut that we'll do during our threading. I recommend 300 and 120, and it is expressed in thousandths of a millimeter. It means that at least we will make a pass of 1/10 or 1/10 and 2. Then we have R, shows excess material at 0.05 left by the finishing pass. R would be useless, unless we set P01 for a finishing pass. Next, the second block has X, Z, R, I, Q, F. F is the pitch, so 2Z minus 20 is the length of Z at the end of the thread. If this length is 20 and you start from Z4 at the bottom of the thread, note the diameter at the bottom of the thread, and R, the diameter variation between the start and end of the thread. Then we have the second block, where we have X, Z, R, I, Q, F. So we already tell you that F is essentially the pitch. So 2Z minus 20 is the length of Z at the end of the thread, meaning if this length is 20 and you start from Z4 at the bottom of the thread. Let's take a second to specifically write down the diameter at the bottom of the thread and write R, the diameter variation between the start and the end of the thread. So if the diameter is cylindrical, R will be 0, and we'll be making a cylindrical thread at this point. Let's take a second to write down the diameter at the bottom of the thread and write R, the diameter variation between the start and the end. of the thread. So if the diameter is cylindrical, R will be 0, and we'll be making a cylindrical thread. P is the depth of the thread in radius. If this is the thread, this is P. In the threads, in metric threads, P is equal to 0.6 times 2. In hitchwork, P is equal to 0.65 times 2. General rule, to avoid doing too many calculations. So, pitch of 2 will have a P of,
because it's in thousandths of a millimeter. If this height is 1.2 millimeter and the crest diameter is 20, the final diameter is 17.6. Now 300 is the depth of the first pass. For the first pass, it's in radius. If I have a thread with a diameter of 20 millimeter, I will make the first pass at 19.4. Okay. That's why I'm writing 17.6. 300 is the depth of the first pass. I think it's in radius. With a 20 meter thread diameter, I'll make the first pass at 19.4. Setting 300 in radius means 300 times 2 is 0.6. Changing these parameters modifies the number of passes. Other passes are calculated using a formula you might have screenshotted. I've done a lot of threading with G76. On controls like CS, the macro is different. It doesn't give Q, but gives the number of passes. You divide the thread height by the number of passes. The macro is rigid. G33 allows one pass. G33 is generally understood by everyone. If I set 300, because being in radius, 300 times 2 is 0.6, so I'll take away 3/10 for the first pass. By changing these two parameters, especially this, 1, I will modify the number of passes. All the other passes, like the half passes, I calculate using a formula that if you took a screenshot of earlier, you'll see, but you don't need to memorize it now. I've done a lot of threading, but with G76. However, for example, when you work on controls like CS, everything I explained is conceptually fine, but the macro is completely different. For instance, it doesn't give you Q like before as the final pass or initial pass, but it gives you the number of passes. So you can make passes, the number of passes, meaning you divide the height of the thread by a certain number of passes. Everything is the same, at least on the very old CS systems I used to work on. So this macro is quite rigid. I explained it according to Mama Fanook. Remember, if you have any doubts and can't figure it out, G33 allows you to make one pass. If you want to make 10 passes of a tenth, you can do 10 passes of a tenth and manage your threading using G33. G33 is generally understood by everyone. CNC. Now from my explanation, you understand that this is a fixed cycle that I don't really like. Just because you don't like something doesn't mean you shouldn't use it. Here you can see the fixed cycle, which is, thank goodness, the rough copy of what we've written here, or rather the nice copy of what we've written here. Let's go ahead and simulate it, and as you can see, I've turned the machine around. Let's do it together and rotate the image according to the position that interests us. Let's restart and go to start. Okay. You see that I'm getting ready to make the first pass at 19.4. 20 minus 0.6 and then all the others. You see 19151, he does a mathematical calculation to make all the passes. Now, let's modify the Q300 and set it to 1000. Alter, simulate, restart, and start. You see that? In 2 passes. It solved the problem for me. Because it obviously did the calculations according to 1120. If I were to put 1250 here, it would probably generate an alarm, because it says I can't make a depth greater than the depth of the thread. So let's check it out. Sometimes making mistakes helps. Let's put 1500. Alter. Simulate. Restart. Start. It did it like that too. So, be careful not to mess up this number. It's strange that it doesn't give me the alarm. Sometimes even Fanuc thinks incorrectly. You made a mistake writing it. The beauty of the Fanuc manual guide is that even the good old cancel button is easy to find. Here it is. Cancel. Cancel. And you see that Q300 goes back to its original value.
It was perfect before. I'd say we've seen all the facets of this threading tool. Now, one thing, if you find yourself needing to do internal threading, the positioning X doesn't change much. It will be here. This X will be here, and everything else stays the same. Let's go read what we've written here. The values of Q and P are unsigned, so I don't have to worry about changing the sign of P and Q when working inside or outside. No, they're always unsigned. I just need to modify this point, that is, the end point and the finish point. No, they're always signed. I just need to modify this point, that is, the end point and the finish point. Eventually, for tapered threads, I'll also have to adjust the R so that it threads like this. They're rare, but you can also find tapered threads. Eventually, for the conical threads, I will also have to modify the R in such a way as to make it thread in this way. They are rarely found, but conical threads are also found. Then there are front threads and other types of threads that I won't cover in this course, because honestly I'd struggle to explain them on the board. I don't know if you've noticed, but I find it much easier to explain direct point-to-point programming than using fixed cycles. This is because fixed cycles are very convenient, but they're fixed. So, if I need to rough out a fixed cycle, my fixed cycle will always do this. Once it gets here, it will keep following the profile. But if I program in ISO, I can decide that once I get here, I can break off directly, break off directly, break off directly, break off directly. This leads to a huge time saving. I've worked in high volume production, so time is important. If you're making a single piece, the fixed cycle will be your lifeline, or even for small batches, because programming time becomes a significant factor in cost estimation. But if you're making 100,000 pieces, it's worth it to have a program that's 100 lines longer, but saves 3 seconds at the end of the cycle, especially when you're producing 100,000 identical products.
Time, money, and production are key. Followers know I prefer long programs over fixed cycles. I use fixed cycles for threading because they're convenient. Fixed cycles are good, but direct programming is better. I'm making a video on threading. Programming is important, but securing the spindle is vital. This job has many facets, and it's impossible to explain all. Every company has its secrets. A good turner in a valve company might struggle in a bar stock company due to different challenges. There's always something to learn. I was told we work with Lincoln and super alloys because the future of turning in Italy is tackling difficult tasks. Simpler tasks are left to others. Threading video, programming matters, but spindle security is key. Companies have secrets and methods. A valve turner may struggle with bar stock due to different challenges. Always learning in this trade. After 20 years with cast iron, I learned about Lincoln and super alloys, the future of turning in Italy. New fascinating work. Super alloys are captivating, but tough. Wrong tool choice is disastrous. Thanks for watching. See you in the next video on fixed cycles. Every company has its secrets, and each type of part production has its own methodologies. So, a good turner in a company that makes valves for the petrochemical industry might be a terrible turner in a company that makes small parts from bar stock, because the problems faced when making a 1 meter diameter valve are completely different from those encountered when working with a bar stock machine or a multi-spindle machine. Sorry, I couldn't remember the term that makes parts with diameters of 1, 2, 3, 4, 5. So there's always something to learn in this trade. Many times I also have to ask for help. 3 years ago, after 20 years working with cast iron, I was told, guys, here we work with Lincoln and super alloys because the future of turning in Italy is about doing difficult things. The simple, stupid, and trivial tasks without taking anything away from them. We let the Indians and Chinese handle those. I found myself discovering a completely different way of working from what I learned 20 years earlier, and it's actually more fascinating because working with super alloys is indeed captivating, even though it's not easy. If you choose the wrong tool, you're done. Sorry for digressing from the main topic of today's tutorial. I thank you for being with me, and I look forward to seeing you in the next video where we'll cover fixed cycles. I found myself discovering a completely different way of working from what I learned 20 years earlier, and it's actually more fascinating because working with super alloys is indeed captivating, even though it's not easy. If you choose the wrong tool, you're done. Sorry for straying from the main topic of today's tutorial. I thank you for being with me, and I look forward to seeing you in the next video where we'll cover fixed cycles. Frontal and radial rules, and then we move on quickly. Thank you, and see you next time. And then we move on to tamburba. Pay attention. Thank you, and see you next time.